Okay, hello everyone and welcome to Makeland 360. In this video, I want to solve a question with you to illustrate the concept of the Euler load. Um, but in this question, we've been given a cross section. Um, so let's look at the problem together. So we have been asked to calculate the Euler's critical load for a strut, which is T section. Now the flange, so this is the flange, that's area 1. It has a width of 10 centimeters and then overall depth of 8 centimeters, and then both flange and stem is 1 centimeter thick. If you look at this, you can clearly see that this is 1, this is 2. So the 1 is the flange, and then the stem is the, and the 2 is the stem. As a matter of fact, it is having a certain um depth, okay, but the depth will go inside, okay, the depth will go inside. If you look at the cross section, we will only see the T. All right, okay, so the strut is 3 meters long and it's built in at both ends. So essentially, when you hear built in simply means fixed at both ends. So fixed, that's the meaning of built in. It means it's fixed. So fixed at both ends. Now before we even come to this side, we have to first of all calculate the area moment of inertia. As a matter of fact, this figure here is sort of going to help us to calculate the area moment of inertia before we can even think about the Euler load. Okay, so without wasting much time, let's first of all look at the area moment of inertia given this cross section. Okay, so but then let's first of all look at this, the x-axis. So this is what I'm trying to say. The x-axis is not somewhere here. Okay, so the x-axis is not somewhere here. It is actually at a certain distance from the origin, let's say O. So we need to find this distance. So this distance all the way from the ground. So essentially, we want to calculate the whole of the distance from O to the XX. They have done it and they got 5.85. But I want to do it with you. So let's do it together. Y bar is going to be summation AI y bar I divided by summation AI. So essentially is going to be that's going to be A1, which is the flange, having an area of 10. Okay, so the flange is having an area of 10, but then, or let's say 10 times 1, but it's the same as 10, so that's why I don't write times 1. Okay, let me write it so that everybody will be happy. So 10 multiplied by 1. But what is the y bar? Now when we say the y bar, we are talking about the distance from the origin, which is down here, all the way to halfway of the flange. Okay, so okay, let me write it this way. So A1 y bar 1 plus A2 y bar 2 divided by A1 plus A2. So the first A1 is the 10 times 1. And then the y bar 1, you have to walk all the way from this origin until you get to halfway of the flange. And essentially, that's going to be this 7, which is here, plus halfway of, 1. So that's going to be what? 7.5. So that is basically for the flange. And then you do the same thing for the stem or the web. The area is going to be, the whole of this length is 8. So 8 multiplied by 1, that's sort of the area of the stem. Then you multiply by, from the origin halfway to the stem. That's going to be halfway. So what do you think? So it's going to be halfway, but I want us to look at it in this sense. The area 2 is actually this here, okay? So if you look at it carefully, the area 2 is not the entire length, but then that one which is in the middle, okay? So that is the area 2. It is not the whole of this. Please take care of this. So but then I want to bring your mind to this. So there is a problem with the diagram. As a matter of fact, the entire distance from here to here is rather supposed to be 8, and then this is 7, so that if I add 7 to 1, I get 8. Okay, so in effect, the cross-sectional area is supposed to be 7 times 1, because then the whole of this is 8, and then 8 is the same as 7 plus 1. So here is 1, but then here must be 8. Okay, I think it was just a typo error. Now let's come to y bar 2. So y bar 2 will be working all the way halfway through the second one. So it's going to be half of 7, which will be 3.5. Then I divide by the areas. So 10 plus 7. Now if I do this, then I will get the y bar, which is the distance of the actual centroid of the whole figure. And that's where I will look at when I am calculating the area moment of inertia. So let's do this together. So this is going to be what? 10 multiplied by 1 multiplied by 7.5 plus 7 multiplied by 1 multiplied by 3.5 divided by 10 plus 7. And what's that? So essentially that's 5.85. So you see where the 5.85 is coming from. So that's where it is actually coming from. Okay, so that is it. Now that we have gotten this, the next step is that we know that this is our x bar, our sort of the centroidal, how do I put it? So this is actually the reference axis. Okay, so this is the reference axis which we are going to use for our calculations, but the y is still passing through, so we will use that one. I hope the concept is clear. So at this juncture, I want us to calculate the area moment of inertia, since we now have our reference axis. So let's start first of all with the ISS, like that's the moment of area about the x-axis, okay, or the horizontal axis. Now we would have to use this x-axis here. But what do we know? So we know that if I have a rectangular cross section, then the area moment of inertia is BD cube out of 12. Now B could be anything and D could be anything, but sometimes some of the textbooks would want to say the width and then the thickness. But essentially, if I have this, then the B is this side and then the D is this side. In some of the textbooks, you will see B H cube over 12 is the same thing. Okay, so whether D or H is the same thing. All right, so now we are going to use this formula, which is the centroidal area moment of inertia, and then we will add what we call the parallel axis theorem. So let me start with a flange. Let's draw an imaginary x-axis through this flange and call that xc. So that xc is more or less like the centroidal x-axis of the flange. So right now you calculate this distance all the way from the flange to the x-axis. So this is what we are saying. To calculate the ISS, it is going to be so let me do it this way. So it's going to be ISX1 plus IXX2. So IXX for the first shape, which is the flange, plus the web. So considering the flange, it's going to be BD cube over 12. And that's going to be pretty much simple because it's going to be 10 1 cube divided by 12. Now if you do this 10 1 cube over 12 is only the centroidal, but we have to add what we call the parallel axis theorem. So parallel axis theorem, and that is nothing but saying that there is a distance between the centroidal x-axis and the reference. To calculate that distance, don't forget that we just said this is 5.85. But what do we know? So we know that if this is 5.85, then when we so let's do it this way. From here to here is 5.85. But what is the distance above this? Simply put, so the simplest way to do this is to know that there is this halfway of 1, which is what? 0.5. So we know that halfway of 1 is 0.5. But what is the remaining distance so that we can add to the 0.5? Okay. And that is going to be 7 minus 5.85. So 7 minus 5.85. So 1.15. So the 2.15 is the extreme, but we just want just halfway. So that is it. It's going to be 1.15. So 1.15, which is basically that distance till we get to this end, and then we add 0.5 to it, and that will give us 1.65. So essentially this is what we are going to do. It's going to be plus the area, which is 10 times 1, and then d square. So the d is going to be 1.65. So when we say d, we are talking about the parallel axis theorem. And then we are going to do the same thing for this beam. For the flange, the web, for the web. I've taken my time to explain so that you get it. So we are now coming to the stem or the web. So the stem is also going to be the same thing. We will start from this end here and then do the same thing. So if I look at this term, it's going to be something like this. So the B will be this side, and then the D will be this side. So it's going to be 1 multiplied by what? 7 cube out of 12. So 1 multiplied by 7 cube out of 12. And then we are going to do the same parallel as this. Now, you want to ask yourself, what is the centroidal x-axis of the stem? So if you look at this stem, the whole distance of the stem is what? The whole distance is 7, but halfway of 7 is 3.5. So let's assume that this is the centroidal x-axis of the stem, but the reference axis will be what? Don't forget that the whole of the distance from here to here is 5.85. So if this is 3.5, then what will be here? So we just have to subtract 5.85 from what? Sorry. Yeah. So 5.85, you have to subtract 3.5 from that. And if we do this, we will get exactly that distance. Okay. And that distance is 2.35. So essentially, this distance here is 2.35 centimeters. Now, what we are trying to say is that we will add, so it's going to be the area, which is what? 7 multiplied by 1. Then I will multiply it by d squared, which is 2.35 squared. So as a matter of fact, this is strength of materials 2. But in strength of materials 1, you did area moment of inertia. So this is where you apply it. I could have gone straight forward, but I have taken my time to explain so that you understand it. Okay. All right. But I don't need to explain this to you because you have already done that in your first course in mechanics of materials. Okay. So now that you have the ISS, let's add everything together now. So that will be 10 multiplied by 1 cube divided by 12, and then 10 multiplied by 1. So we don't need to add and again, and then we just multiply by 1.65 squared. Okay. So that is like the first part. Then let's add the second part. So the second part will also give us 1 times 7 cube divided by 12 plus 7 times 2.35 squared, all into bracket. So that's 95 point, let's say 30. So 95.30 centimeters to the power 4. So essentially that's like, if we do the x-axis, that's what we are getting. So let's again do the y. Why are we doing this? So first of all, you calculate the x and then you calculate the y. After that, then you look at the least, because the least moment of area will give you failure first. Okay, think about getting a small number and a bigger number. Which one will first occur? The small number will first occur. So we'll use the least, but let's calculate the IYY. So for the IYY, it is going to be pretty much straightforward. Okay, so IYY1 plus IYY2. So IYY1 will be the IYY of the flange. But if you look at the flange, you see that for the flange, the whole as a matter of fact, the y-axis is passing through the centroid. So what this means is that we don't have to waste our time to do the parallel axis theorem, because the axis, which is the reference y-axis, exactly coincide with the centroidal y-axis. Okay, so that is it. We will not calculate the area. We will not calculate the parallel axis theorem. However, we will still do b d cube over 12. But because we are going to do IYY, this time around, it's going to be the b will now be this side. So the b will now be this side, and the d, so it's like now, because you are dealing with the y, the b will now become the vertical side. So please take notice of that. If it is ISS, it will be b d cube over 12. But if it is IYY, it will swap. Okay, it will swap. I don't want to say b cube d, but it will swap. Think about it that way. So for this example, the first one will be 1. So instead of 10 times 1 cube, it will be 1 cube. It will rather be 10 cube times 1 divided by 12. That's all. And then for the other one is going to be, for the first one it was 1 times 7 cube, but this time around it will be 1 cube times 7 divided by 12. So think about it that way. Whenever you do the s and you are coming to do the y, it will swap. That's all. But because the centroidal axis passes through the reference y-axis, we don't need to calculate for the parallel axis theorem. Okay. If you have a question, please leave it in the comment. I will look at it. Now, so let's calculate this. So IYY will then become 10 cube divided by 12 plus 1, which is the same as 1 cube, multiplied by 7 divided by 12. And this gives us 83.917. 83.917 centimeters to the power 4. So essentially, this is our IYY. Now, you ask yourself, this ISS and this IYY, which of them is least? Or in other words, which of them will occur first? We have 83 and we have 95. As a matter of fact, 83 will occur before 95. So the I which we will use in our calculation will be the least, which is the small one, because that is what is critical or is going to happen first. I hope the concept is clear. So now I will be the one we have chosen, which is 83. So 83 0.917 in terms of millimeters to the power 4. All right. So yes. So that is it. Now, at this juncture, this is what we have to do. Because the question said the strut is built in. So let's go back. He said built in at both ends, meaning that it is fixed at both ends, right? So that is it. Now we will have to calculate the Euler load. So you see that this question is not difficult, but the whole idea is to bring you back to what you have done in your first course in strength of materials. Because if you don't understand how to calculate the moment of area from this, please, you cannot solve the question. Okay. So PE will be pi squared, that's the Euler load, EI, divided by LE squared. But the LE is the effective length, which will come from the end condition. Now, because this is fixed at both ends, the end condition will be L over 2. The effective length, sorry. So the effective length will be the length divided by 2. From the question, he said the length is actually, so the strut is 3 meters long, which is the same as 3000 millimeters. So this one is going to 1500 millimeters, right? We don't need to punch this one too. So the Euler load, and then we were given the value for the Young's modulus as 2 times 10 to the power 5. So pi squared 2 times 10 to the power 5. The I is 830.917 divided by this L is, which is 1500 squared. So basically you end up with pi squared 2 times 10 to the power 5 multiplied by 830.917 divided by 1500 squared. 728.962. So 728.962. And that's actually the Euler load in kilonewtons actually. So that is the Euler load for you. Thank you very much for watching. If you have a question, you can drop it in the comment section. Thank you.